Hi guys, today I will give a talk about fuzzing the variety of web servers you may find on the internet. So let's start. First about me, I'm a penetration tester at digital security company from St. Petersburg, Russia. My main responsibilities is to perform a penetration testing of web applications or mobile applications and corresponding infrastructure. So let's begin with the talk. During a regular penetration test, which any pen tester could do, there's a huge chance to run into some totally unknown HTTP software. Most likely it will be web proxies of some sort. No, or at least it was in my first case. I suddenly see some terrible unknown software, and it was a web proxy, exactly the tunneling web proxy. So at this time I asked myself how to check such software for some binary vulnerabilities in a fast way. And the simple answer appeared in my mind, and this answer is fuzzing. Of course, I started from some Googling. For example, I found the famous Sully framework, which contains some built-in descriptions for fuzzing generic HTTP requests. Also, I found a tool named Patot for Patot, exactly the daemon that fuzzes the responses of HTTP protocol, and its counterpart, Patok, the tool which is exactly mutates requests, HTTP requests. Also, there is a plenty of commercial fuzzers, for example, Cryptonomicon, but they are too expensive and I cannot afford it. So not so much tools found it this way, or maybe just my Googling skill sucks, and I decided to write my own fuzzer, so we should talk about it. There is exactly a great number of different types of web servers used in different types of ecosystems to perform different kinds of tasks. On this slide, I'll try to cover some types of such as web servers. As I told in the introduction part, first of all, I started to fuzz for binary vulnerabilities in web proxies. So the first type of web servers will be web proxies. What is web proxies? Web proxy acts as an intermediary between an actual web client and an endpoint web server. So the web proxies may be used for example, content filtering. Such proxies provide some functionality to control what user may or may not see. For example, it may filter content based on URLs, MIME types, actual contents being sent or received via the HTTP protocol, and so on. As we can see, there is plenty of points where we can manipulate this data being analyzed by such a proxies. The next types of web proxies is tunneling proxies, which primarily used to, for example, encrypt some plain text data into the encrypted tunnel. Or it may be used to, for example, secure the connection from an internet to the corporate intranet. This list definitely is not complete, but gives quite an idea of what web service or web proxies do. So the next type of web service is web servers originating on embedded systems. Servers of this category basically used to perform some administrative or monitoring or other system-related tasks. And the first group in this type of embedded systems is network devices such as routers and other network devices. For example, you can find such devices even in Starbucks cafe or something like that. The next type of devices is industrial devices, for example, industrial controllers or industrial routers. These devices follow the latest fashion and embed the web servers to simplify the administrative process for network engineers. So this might to be fast as well, etc. Also, I have given this another type of web service, which actually is not an independent type of web service, but actually is some custom modules or experimental modules which is developed for mainstream servers like Light HTTPD or Nginx or Apache. For example, there is a vulnerability in experimental model for Nginx server in the model of Nginx HTTP SPDI. And the last category I called the other. I put to this category any kind of software which I cannot put in any of the previous ones. For example, to this category we may add any CIM systems or some web streaming servers. And that's all for web servers for now, but there is another type of software which uses HTTP protocol to receive and request and receive data. And these types of software is clients. Clients also may be fuzzed. For example, it may be some security scanners or user utilities like CURL or wget. I think that I should give a brief description for HTTP protocol, just because it's the exact protocol that I be in Fuzz. So the HTTP protocol is usually a plain text protocol which consists of simple requests and responses. A standard HTTP request looks like you may see on the screen. It contains some segments logically separated from each other. For example, first segment is a first line which contains method definition, relative URI, sets of URL parameters, and the HTTP protocol version being used. The second segment of data is headers data. The header is a pair of name value pair separated by a colon. Each header must be on its own line of the request. And after the header section is over, there must be an empty string. The next segment of data of request is a payload segment. There, any client may put some data it want to transfer to the web server. And if we have a request such a payload, there must be also a content length header contains exactly length of the payload being sent. So I think that I almost forget. Each line of the request must be separated from each other, but CRLF characters, so the parser may determine which line it is analyzed right now. So let's look at each segment in details. First segment is a first line, which contains of method definition. Methods may be standard, for example, get, post, head options, etc., or some WebDAV methods, for example, copy, move, lock, etc. Also, there may be some custom methods that defined by developers of exact web server, and the number of such methods can be limited only by imagination of an actual developer. So, while web server definitely passes the methods to decide what should it do with received request, it of course may be prone to some vulnerabilities during such parsing. So method is a fuzzable parameter of the request. Next is the URL path. It also needs to be fuzzed because there is maybe some bugs during parsing. For example, long URLs or URLs consisted of large amount of parts separated by slashes, or any part may be too long and also may cause some bug. So it must be fuzzed also. The third set of data being fuzzed is the parameters data. Parameters data is a set of name-value pairs with equal between them. Each pair is separated from each other pairs by an ampersand. So it must be fuzzable, must be fuzzed also because such parameters may lead to some behavior which cannot be which we cannot get by any other means. For example, using such parameters, we could call some API or some random binary, for example. The last thing is the protocol version. It may contain, it contains the current version of protocol being used. For example, it may be 0.9, 1.0, or 101. This type of data not usually being parsed in such way, so there may be some bugs. So fuzz or not to fuzz, it's up to developer. I prefer not to fuzz for now. There is another notable part of the request that is server name plus protocol scheme. This part of the request used only if the client uses proxy web servers to connect to actual endpoint server. So web proxy will analyze such a URL to resend the request being received from the client. So these parameters also should be fuzzed because, for example, content filtering proxies may analyze such a string for some blacklist. So fuzzable. The next part we should discuss is the headers part. As I said before, each header consists of name and value separated by colon. Each header contains on its own line and separated from each other by CRLF. So, first of all, headers values. Header values may be any kind of, contains any kind of simple data. For example, strings, integers, both unsigned or signed. It may contain some complex data, for example, multiple string values or even a combination of strings and integers. This is an example of such a complex header, the cookie being sent to the google.com without any authentication. So whereas we can see two separate cookies separated by semicolon. Also, there is some magic data. I don't know what it do. No matter. So, as a web server definitely will parse these values, they should be fuzzed. And that's all about the headers. Each header value pairs also must be fuzzed. So, for example, we may duplicate each header a number of times, which may reveal some additional bugs in the HTTP parser on this web server. Or we can, for example, fuzz delimiters between host and between name and value, etc. So it must be fuzzed also. The next type of the next segment of HTTP request we need to discuss is a data segment. Here we're gonna talk about two different types of data being transmitted in the data types. First is the default types and its names you can see on the slide. So if this type of data is used, then the post data is exactly the same as the URL parameters followed after the path. So it should be fuzzed exactly the same. The next type of data is a multi-part. Multi-part is mostly used to transfer data such as transfer binary data, such as, for example, images or archive files, etc. Here, the resulting payload of data type of this type consists of several MIME messengers. Each represents an actual parameter being sent to the server. Each MIME messengers consists of some headers, some values, which we should discuss right now. And first to mention is a content disposition header. It may contain a value, one of predefined values, for example, form data, attachment, or inline. And a number of some custom values may appear here also. So we need to be fast because it may causes some bugs in the parsing of HTTP request by web servers. The next thing to mention is the list of parameters being transmitted within each MIME message. For example, these parameters may be a name of parameter or a file name if we transmit a file. So these parameters may contain any data you can imagine and may be named anyhow you can imagine, so fuzzable. And the last thing I want to mention is exactly data which is being sent in the each MIME message. For example, there may be transferred plain text data or for example integer data, and it should be fuzzed accordingly, like strings or integers, so fuzzable. And the second type of data is the binary values, which is used to transmit, for example, files, which also need to be fuzzed, but in some different way. I will try to cover it a little bit later. So fuzzable. That is how a typical request looks like, and we need to don't forget to fuzz all the delimiters we can find in the request, because while parser is looking for a delimiter, it may separate one type of data from another type of data, or parsing a number of delimiters, it may think that there is a number of different values for an example of host. So it must be fuzzed too. Okay, let's talk about fuzzing approaches, the approaches that are used to fuzz web servers. And the first approach is a straight client originating fuzzing. In this approach, a fuzzer pretends to be a legitimate client, which is sending some request to the web server. The web server then asks with a response of some type. For example, it can provide a normal data or some errors, or there may be an errors generated by on socket level. If so, then client should log all the requests being made. So the scheme is quite simple. First, client sends a fuzzed request, one at a time. Then web server try to analyze that request. If it can do it, then it will somehow respond to that request. Otherwise, web server, for example, will crash or consume a large amount of memory and will crash a little bit later. So in that case, client should use some monitoring service to determine if web server is alive or not. And in any other ways, web server will answer the request and send its response to the client. So the process repeats a number of times. The second approach is a so-called reverse fuzzing. The main concept of reverse fuzzing is to send fuzzed data in the response to the valid request from, for example, a client or a HTTP proxy, and so on. So the process look a little bit different from the straight fuzzing and looks like this. Client sends a legitimate HTTP request to the web server. Web server then gets another fast request from its own list of generated data and sends it to the client. Client gets the response and may fail or may not fail, and we cannot determine exactly by during we cannot define the client's behavior on the web server side without no additional methods. So there is some difficulties to fuzz in this way. First difficulties is how to check client's health without not directly communicating with it. So there is some methods, we discuss it later. And second difficulty is we need to restart, not restart, but rerun the clients after each successful request. So it may send another request and another request. And the third approach of fuzzing is somehow like a culmination of previous two methods, and I call it double fuzzing, mostly used to fuzz the HTTP proxies. And the process looks like this. The client sends fuzzed HTTP request to the proxy. Proxy tries to parse it. If it fails, then it fails. And the client should know about due to some errors or socket errors, etc. Then if everything seems ok, HTTP proxy resends the HTTP request to the web server, which is actually a fuzzer. Web server then totally ignores request being sent from HTTP proxy and generate its own fuzzed response and send it back to the HTTP proxy. HTTP proxy then may or may not be crashed. So if HTTP proxy crashed, client will know about it and may tell the server. So if everything seems okay, HTTP proxy respond to client with a fuzzed response from the web server. So it allows us to perform all kind of tasks on a single scheme. For example, we could fuzz HTTP proxy from a client perspective and fuzz HTTP proxy from an endpoint web server perspective. Now a few words on detection of some anomalous activities of target process, of crashes and so on. There is a number of detection methods. First of them is traffic analysis. In my research, in my tool, I do not use that method, but I think I need to mention it anyway. So in this method, you can, for example, analyze data on TCP level or HTTP level. You can look for some RST packets, for example, or some timeouts. In this method, the monitoring process, which is analyzing the traffic, must be placed somewhere near the actual client and the fuzzy target, so it can process all the traffic being sent between them. The second approach is to use a local processing monitor that must be placed on the same machine, on the same physical machine as a target. Once the monitoring process placed on that machine, the monitor must do the following things. For example, it needs to watch for system calls being made by the process. It must watch for some file system activity or any other resources activities on target machine. Watch for unusual signals being sent between target process and the system. For example, segmentation fault. Also, it may watch for allocation of memory and some anomalous allocation of memory. Uh, the last method is some heuristic based on responses get from target. So this method is based on exactly the request response mechanism between client and server. In this method, I placed some types of analyzing methods. For example, analyzing HTTP error codes which target web server sends to us, or maybe intermediate proxy sends to us. For example, it may be 502 or 503 errors, HTTP error codes. And another method is to analyze socket errors. For example, connection reset by peer, connection refused, or software caused connection to abort. So this method is not ideal, but gives us quite an idea of what's going on the target server. So there is one additional approach I placed in the heuristic based on responses. This approach is to compare with reference response. So just before performing the fast testing, the one tester, for example, needs to harvest as much valid requests and responses from the server as he can. So performing each request fuzzing, he knows which response should server give us for each fuzzed request. And if reference response and the exact response differs, it may lead to some bugs and needs a manual investigation. So, some words on my tool which I implemented for performing fast testing of web servers. But better, I think it's not a tool, but some concepts implemented with some programming language. So first of all, which model should a typical fuzzer have? First of all, it's a generator, which generates data. It's obvious. Second module is a transmitter model, which transmit data from generator to target and gets the responses from target. And the third method and the third module is the monitoring module. Now let's look at each module in more details. First generator, as is already said, is generate data. In my generator model, I use some fuzzing primitives from a Sally framework, for example, integers generators, string generators, or delimiter generators. Also, generator may contains fuzzing primitives to generate binary data. And for this purpose, I use a tool named PyZoof. PyZoof is a Python implementation of Zoof general purpose fuzzing. And here's a bit of advertisement. So PyZoof, you may find it here. Its author is Nezloy. So you may look and check. For now, I assume that given fuzzing primitives, integers, strings, etc., will be enough to describe each types of more complex generators. For example, headers. I also create some headers generators. For example, accept encoding, content encoding, which is similar to accept encoding, accept language, accept charset, range headers, or for example, authorization header. Each generator takes as an input value the actual value of the fuzzing header. For example, for host, it may be localhost. And then mutates it in all the possible ways determined by generator. For example, if it is an integer, it may generate max integer, max long, min integer, min anything else. So in the bottom line, I have fuzzing primitives, which is, as already mentioned, integer, strings, etc. More complex header generators, which, for example, also may generate multiple sets of parameters. For example, if you look at the cache control header, there is a parameter with integer types and the parameter with a string type. So these types of header must also be generated with a generator. Also, my Fuzzing contains a generator for URL string, including a path generator, which generates each part of the path as a string, and a separator of path slash as a delimiter. The second kind of URL path generator is a URL parameter generator, which fuzzes values of each parameter, name value pairs as a single entity, and also fuzzes the delimiters of each pair and between pairs. Also, I have a generator to generate post data that is transmitted via the payload. So, for example, there is a two type of data being generated that way. First type is a default type, as already mentioned before. In this kind of post data, the generator is exactly the same as a URL data. Exactly the second part of URL data, URL parameters. And the second type of post data is binary generators, which may be used, the result of whom which may be used to as an independent entity or as a part of more complex multi-part entities. So I think that's all for the generator. The next module is a transmitter. I think it is a core module of fuzzers. So it gets that fuzzy task from a generator via the queue and then sends it to the target. After the fuzz request being sent, transmitter must get the response from the target, and that's the second role of the transmitter. It should somehow analyze the behavior of target by analyzing the exact answer, or as already mentioned, some socket errors. If some anomaly occurs, transmitter must log. First, it logs each request being sent to the target, and the second, it's safe to log each request that causes anomalous activity on the target. So having both log files, for example files, we could always understand if there is a single packet that crashed the target, or for example there is a chain of packets, each of whom must be sent to target to crash. So that is all transmitter do, and the third model is a monitoring model. I already discussed it on previous slides. The monitoring model may be put on the same machine as the target, and so it may analyze the behavior of the target on that machine. Or monitoring model may be put somewhere in the network between transmitter and target. Anyway, then monitoring model gets some statistic on target behavior. If any anomalies occur, monitoring model should immediately send these results to the transmitter, so transmitter can understand why and what happened to the target. You can find my Fuzz on the GitHub, but for now it's out there, but I think I will release it after the conference in a couple of hours. So check the link. Some other feature of my Fuzzer, it contains a number of fuzzing modes, for example, HTTP header fuzzing, URL data fuzzing, post data fuzzing, or so-called whole request fuzzing, which is used to fuzz the given request as a single entity. For example, it may multiply headers, may multiply URL data, may multiply delimiters or delete all the delimiters, and so on. So also the fuzzer have an option to fuzz the given method, HTTP method. It can be used to fuzz, for example, one single method at a time, or it may be used to fuzz all the possible HTTP methods that you must describe in the config file. So Some other options of my fuzzer is, for example, multi-threading for greater performance, and then another interesting option is delay. Delay, as I discovered, some web servers lack the ability to handle a number of simultaneous connections from a remote client. So to successfully send another fuzzy request, we should wait while target server closes the socket descriptor. So the delay here will help us. So some examples at the end of my talk. Right now, I'm in the middle of the research of vulnerabilities on a number of web servers on the internet. I try to release the research somewhere in the middle of June. I hope so. So, first of all, I would like to mention a group of bugs which have the same origin. The bugs appears in the wrong parsing of content length header. For example, some parsers will parse negative values in content length. For example, -2. And due to this incorrect parsing behavior, there may be some integer overflows because that negative number, so signed int, is translated to the unsigned int, and we get a great large number. And with this large number, for example, we could overflow a buffer which is set for us for the data being sent by the developers. Or, for example, some parsers may try to process content length of extremely large numbers of values, for example, max long. And this may also cause a buffer overflow, for example. So, the first bug is a bug I found on some video streaming server. Bug occurs while parsing content length header with the parameter -2. While parsing such a request, a web server tries to convert signed integer to an unsigned integer, so it gets a large number, and then it tries to use allocation function to allocate such a big value, so it's caused a memory consumption bug. Next, here is a bug with a content length header specified in 601. This is a funny bug because the developers of web server used a secure string copy function, which, if something goes wrong, which is give us an exception. So it's the good part. The bad part is that developers forgot to handle that exception properly, so then exception occur, the server will crash, so it's sad. This next bug is a bug with any negative value. It was found in one of the custom modules for an IIS Microsoft server. And the bug causes an integer overflow vulnerability, which is in its ways causes a stack buffer overflow. The next bug is a bug in an authorization header with a basic type of authorization. If we provide an extremely long login name, for example, 16 kilobytes, this will cause a string. This will cause a unsecure string copy function to override the memory outside the buffer. Another bug which is found in the router is a bug which I cannot debug due to my lack of knowledge in debugging embedded systems, but I hope I will sometimes learn it. So I think, I guess that a large number of entities being transmitted via accept language header causes a buffer overflow in the web server being used on that router. So this is for now all the bugs I have found. But I want to show some more examples. For example, a famous bug in HTTP.C, Microsoft's driver level web server. It causes integer overflow while passing such size of range. And also a CVE in the Calibri web server, which is caused by an extremely long URI in the post request. For example, it must be somewhere in the length of 736 bytes. That's all for today. So, any questions? Okay.
So my question is that you have shown us that the bugs can be discovered by the fuzzing, right?
Yes.
But was there any exploitation, like you override the EIP and execute your shellcode?
For now, in my research, I doesn't found any bugs which may be escalated to the remote code execution. But for example, this bug in the Calibri web server allows you to exploit a remote code execution. Also, yesterday the guys at the OWASP track told about some vulnerability in ROM pager server, which may lead to remote code execution in the cookie.
Yeah, and basically what I wanted to also ask that if you crash the server or basically perform some overflow, it will perform a segmentation fault on the server side. It will only end your connection, right? It will only end your session because each connection is within its own thread.
No, in my experience, if something like this occurs, the web server exactly crashes. So it's no connections from anybody will not proceed. Or for example, if to told about this particular request, the server, while trying to allocate a large amount of memory, consumes all the memory of the target machine, so machine crashes and nothing could happen. Thank you.